Hello everyone. Today we are going to discuss about molecular velocities, types of molecular velocities. Okay. So the velocities, different types of velocities are possessed by the molecules of a gas. In a given gas, different molecules will be moving with different velocities. That point we have to understand first. Okay. So what we're discussing is types of molecular velocities. Yeah. So in this now here, Maxwell, Boltzmann, these two scientists together have given the distribution of molecular speeds. That means the molecular velocities or molecular speeds, we can use the word, okay? Speed or velocity we can use. So the molecular velocities or molecular speeds of the gas molecules are distributed by these two scientists, Maxwell and Boltzmann. They have said that there will be three types of velocities. There will be three types of molecular speeds for the gas molecules. If you take a particular gas, if you are given some particular gas, in that gas, all the molecules of the gas do not move with the same velocity. Remember, some molecules will be having greater velocity, some molecules will be having lesser velocity, some molecules will be having the velocity in between these two, lesser value and higher value. Like this, different types of velocities will be there. So there are three types of velocities. So the distribution of molecular velocities is in the form of three types. By whom here? Maxwell and Boltzmann. So this is called Maxwell-Boltzmann distribution of molecular speeds. See here, now the gas molecules are moving in all possible directions, right? In a given gas, all gas molecules are moving in possible directions. In random directions they're moving. And they collide. The molecules will collide with one another. And also, they will collide with what? The walls of the container. Okay, so inside a gas, if you take a gas in the container, the gas molecules will collide with another gas molecules. First type of collision. Second type of collision will be between the gas molecules and walls of the container. Right, Ma? As a result of collisions, as a result of these two types of collisions, the speed and direction of the gas molecules, the speed of the gas molecules and direction of the gas molecules, both will be ever changing. Both are ever changing. So ever changing direction and ever changing speed will be going on. That is, all the molecules in a given sample of gas do not have the same speed. Same velocity will not be there. Same velocity will not be there for gas molecules. That point we have to understand first. So in this way, we have to understand that there will be different types of velocities for different types of gas molecules in the given gas. And the distribution of gas molecules among different possible speeds was studied by Maxwell, the scientist Maxwell and the scientist Boltzmann. Boltzmann and Maxwell, these two together studied what now? The distribution of molecular speeds. And using the theory of probability. So there is a probability of how many types of velocities here? Existence of three types of velocities they have taken. So the results are mathematically expressed as, so dnu is equal to 4 pi n, okay, of m by 2 pi rt to the power of 3 by 2 into e to the power of minus mu square by 2 rt into u square du. So these all expressions are need not to understand here. So in physics part you will study all these things here. So in physics part, you can study all these things, but in chemistry part, need not to remember, need not to by heart this formula. Okay, ma. So this formula was given by Boltzmann actually. So Maxwell introduced this concept, and Boltzmann has given this formula. So these all things need not to by heart, need not to worry about it. Okay. So in this formula, N indicates what? Total number of molecules. N is what here? Total number of gas molecules, and M is the molecular mass. Molecular mass of the gas. M is what here? Molecular mass of the gas. And this expression gives the number of molecules. The number of molecules what here? dNu. Number of molecules. The total number of molecules what here? dNu. Having speed in between u and u plus du. The change in velocity. Du means what? The small change in velocity. U and u plus du. Between the velocity u and the velocity u plus du. Okay, so the expression gives the number of molecules dNu having the speed between u velocity and u plus du velocity at the given temperature T. A plot means for graph here. A plot of fraction of molecules in the speed range u plus du. Okay, and 1 by n of dnu du against speed u is given by another one form plot is there. That plot is important to study here. So if you study that plot, you'll understand everything about what now the different types of velocities here. So we are taking the plot of what versus what here? The fraction of molecules versus velocity. U is what here? Velocity, molecular velocity. Molecular velocity, and this one is one of fraction of molecules. The fraction of molecules versus the U. This graph we are going to study. This is what now here? Fraction of the molecules. What is my here? So fraction of molecules. So fraction of molecules. So fraction of gas molecules versus what? Molecular speed. Molecular speed means what here? U. U is what here? Molecular velocity. Okay. So this plot we have taken. So here we have taken y-axis here. Here we have taken x-axis. Okay. Now here it is 0. Now, initially, the 0 velocity will be possessed by 0 number of gas molecules. That means what now here? No molecule will be stationary. 0 molecules have 0 velocity. 0 velocity. Means what here? No molecule is moving with 0 velocity, remember. No molecule is moving with 0 velocity. That means what? All the molecules are in motion only. Okay. And suppose I'm taking here 0 degrees Celsius initially. What I'm taking here? Temperature I'm taking T. T is equal to 0 plus 273. How much? 273 Kelvin I'm taking. So at 273 Kelvin, that is 0 degrees Celsius, one curve we got here. This is one curve. Okay. So this curve is indicating what here? At 0 degrees Celsius. So in this curve here, if you observe, what is happening, you check it here. So here, this is the peak of the curve. This is the peak of the curve, right? Peak of the curve. So peak of the curve, okay. And 3 types of velocities they have given. How many velocities they have given? 3 types of velocity. Okay. So actually, this line should not be like this here. I'm drawing here. Suppose if you take 0 degrees Celsius, this curve we get. And if you take 1000 degrees Celsius, this curve we get. And if you take 2000 degrees Celsius, this curve we get. So it is for same gas, remember. For same gas, we have taken these different temperatures. For same gas at different temperatures. So initially at low temperature, at 0 degrees Celsius, the curve is having what here? Peak like this. The peak is like this. And if you increase temperature from 0 degrees Celsius to 1000 degrees Celsius for the same gas, the curve shape is like this. Okay. So now the peak is broadened here. The width of peak increased here. The width of the peak increased. Means the peak, the length of peak, what happened here? Flattened here. We can say simply the curve, peak of the curve from 0 degrees Celsius to 1000 degrees Celsius, what happened here? Flattened. The peak is flattened. Okay. And also the height of this curve, height of the curve decreased or increased? Decreased. Here height of the curve is more. Here height of the curve is less. That means the peak of the curve is flattened at higher temperature. Still, when you increase the gas temperature from 1000 degrees Celsius to 2000 degrees Celsius, still what happened to the peak? The peak has been flattened still. Flattening of peak is going on here, right, ma? So like this, what when temperature increases, what is happening to the curve? The peak of the curve is flattening, getting flattened, right, ma? It is for same gas, but at different temperatures we have taken. So now here, 3 types of velocities I told now. At this 0 degrees Celsius, there will be 3 types of velocities. At 1000 degrees Celsius, there will be 3 types of velocities. At 2000 degrees Celsius also, 3 types of velocities. So how to take 3 types of velocities is that? So this height of the peak means curve is there here, this one. Suppose it is what? One type of velocity. Here, one type of velocity. Okay, this is called UMP. UMP means what here? Most probable velocity. What is MP here? Most probable velocity. So yes, here MP means what here? Most probable velocity. Here V will be taken or U will be taken, your wish. So UMP means what? Most probable velocity, this one at this point. And here you take this one here. At this point I'm taking another type of velocity. It is average velocity. U average. What is called ma? U average. So U average meaning what? Average velocity here. Okay. Next I'm taking here another type of velocity, that is RMS velocity. URMS. So here at this point URMS we have taken, at this point we have taken U average, at this point we have taken U MP. MP means what here? Most probable velocity. So these three types of velocities means the molecular speeds are distributed into how many types here? Three types. At what temperature? 2000 degrees Celsius. At this 1000 degrees Celsius also same lines we have to draw. Same three lines we have to draw. At 0 degrees Celsius also three lines. Three lines indicating what? Three vertical lines indicating what here? Three temperatures, three velocities. Three velocities of the gas molecule here. Here also three velocities of gas molecules. Okay, same gas we have taken. At 0 degrees Celsius, the gas molecules having three types of velocities. At 2000 degrees Celsius also three types of velocities only. Okay, now here what is to be understood is that, see, at this 2000 degrees Celsius, at this given 2000 degrees Celsius, see here, this height of the curve here, from this point if you take one line like this here, so these many fraction of molecules. So this fraction of molecules having what? Most probable velocity. The most probable velocity is possessed by how many molecules here? So this fraction of molecules. On y-axis what we have taken? Fraction of molecules we have taken. So more fraction of molecules having what? Most probable velocity. So how to define this most probable velocity now? The velocity possessed by most of the gas molecules. Okay, the velocity possessed by most of the gas molecules is called what? Most probable velocity, remember. So most probable velocity, this one. This is possessed by large number of molecules, large number of gas molecules. Next, if you take average velocity, see average velocity, you take this one. And here you take this one, URMS. RMS means what? Root mean square. Root mean square velocity. So this root mean square velocity is possessed by, see, less number of gas molecules. So here less fraction of gas molecules. Less fraction of gas molecules, here more fraction of gas molecules. Okay, so less fraction of gas molecules are having what? The velocity called RMS velocity. This RMS velocity meaning what? Root mean square velocity. See here, root mean square velocity or root mean square speed. So here RMS velocity will be possessed by very less number of gas molecules. That means at given temperature, at this 2000 degrees Celsius, if you take a particular gas, suppose nitrogen gas, imagine, in that nitrogen gas at this temperature, okay, very less number of molecules will have which velocity? URMS. Large number of gas molecules will have which velocity? Most probable velocity. So how to define most probable velocity now? The velocity which is possessed by very large number of gas molecules at a given temperature is called what? Most probable velocity. Is that clear, ma? Now listen carefully. If you take on x-axis what we have taken here? Speed, molecular velocity we have taken. Now from left to right on the x-axis, what is happening? You check it here. What is happening on x-axis here? When you go from left to right, the velocity, magnitude of velocity increasing na? Left to right on the x-axis. Now see, UMP magnitude and the magnitude of U average and magnitude of URMS. Which one is having more magnitude? RMS velocity has larger value. That means what? The magnitude of RMS velocity will be greater than magnitude of RMS velocity greater than magnitude of average velocity, which is greater than magnitude of most probable velocity. Is that clear now? So whose magnitude is least here? Whose magnitude is least? Most probable velocity value will be less, but RMS velocity magnitude will be greater. But which velocity, which type of velocity is possessed by large number of gas molecules? This most probable velocity is possessed by large number of gas molecules. Okay, and RMS velocity specialty what? The highest magnitude is for RMS velocity value. So the molecules which are moving with RMS velocity will be moving faster. Remember, the molecules which are moving with RMS velocity will have faster movement than what? Molecules with the most probable velocity. Is the point clear to all? So there are three types of velocities for the gas at a given temperature. In these three velocities here, means among the three types of molecular velocities, which one has more magnitude? RMS velocity has more magnitude. And which one is possessed by large number of gas molecules? Most probable velocity. And which velocity is possessed by less number of gas molecules? Among the three types of velocities, which type of velocity is possessed by less number of gas molecules? RMS. RMS velocity is possessed by very less number of gas molecules. But most probable velocity is possessed by large number of gas molecules. And whose magnitude is least here? Most probable velocity value is least magnitude. And RMS velocity magnitude is highest. So like this, these points clearly to be understood here. So what we have to understand is that at a particular temperature, the molecules will be having three types of velocities. Among these, we have to take like this. For every curve, we have to take first from top of the peak, we have to take what now here? Towards x-axis, most probable. So next we have to take what now here? Average velocity. Next what? RMS velocity. Now remember that among the three types of velocities, our average velocity will be in between what? The value of RMS average velocity. The magnitude of average velocity will be in between most probable velocity and RMS velocity. So this point we have to keep in mind. So it's about what Maxwell's distribution means, Maxwell-Boltzmann distribution of molecular speeds. Okay, ma. Kinds of molecular speeds. So how many types totally? So molecular speeds are of three types. What are they? RMS speed. RMS speed means root mean square speed. Then average speed, and the most probable speed. And first one is what now? Suppose the root mean square velocity we are taking. RMS velocity we are taking. RMS velocity. Now here the speed in kinetic gas equation, PV is equal to 1 by 3 mnc square. Generally, kinetic equation, we know, no? Kinetic gas equation from KMT. We have studied that PV is equal to 1 by 3 mnc square. Okay. So, E is the hypothetical speed possessed by all the gas molecules when the total kinetic energy is equally distributed among them. So, now what we have to understand, the speed is the hypothetical speed possessed by all the gas molecules when the total kinetic energy is equally distributed amongst the gas molecules. The total kinetic energy of the n number of gas molecules is the sum of kinetic energies of individual molecules. Suppose n number of gas molecules are total here. N number of gas molecules there. First gas molecule, second gas molecule, like this, nth gas molecule. Okay. Now first gas molecule will be having kinetic energy. Second gas molecules will have another kinetic energy. Like this, all the gas molecules have kinetic energies now. So the sum of the kinetic energies will be equal to the total kinetic energy of the gas. The total kinetic energy of the gas is equal to sum of the kinetic energies of what? All the gas molecules. So the total kinetic energy is equal to what? Sum of the all kinetic energies. No? So here C1 means what now? For first gas. C1 is what now? Velocity of first gas molecule. C2 is what here? The velocity of second gas molecule. C3 is what? Velocity of third gas molecule. Cn is what? Velocity of nth gas molecule. Okay. So the sum of all kinetic energies will be equal to what? The total kinetic energy of gas. So half of mc1 square, mc square. C is what? Velocity here. C or U we can take. Yes, C is equal to what? U. Remember, velocity. C otherwise U. Anyone we can take. So here half mv square or half mu square. Otherwise half mc square. The C is what now taken as velocity. C1 means velocity of first gas molecule. So half mc square, mc1 square plus half mc2 square plus half mc3 square plus, okay, and so on, half mcn square. So this is what now the total kinetic energy of the gas is equal to sum of the kinetic energies of individual gas molecules. So let C be the velocity possessed by each gas molecule. Okay, each of the n molecules here. Then total kinetic energy is equal to what? N number of gas molecules, total number of gas molecules into half mc square. Half mc square is what? Velocity, means kinetic energy. C is what? Velocity here. So half mc square into n number of gas molecules will be equal to what now? Total kinetic energy. Total kinetic energy. Integrating both the equations, we get what? N into half mc square. That is total kinetic energy. What is here? Total kinetic energy is equal to half mc1 square, that is first gas molecule's kinetic energy, plus second gas molecule kinetic energy, plus third gas molecule's kinetic energy, plus so on. What here? The nth molecule's kinetic energy. Okay, so from all these things, what we can take now? C square is equal to C1 square plus C2 square plus C3 square plus C4 square plus so on Cn square by n. Average we have taken. It is mean. Mean of squares of velocities. Remember, it is what? Mean. Average of squares of velocities. What we got here? Right hand side here. Mean of square of velocity. Mean means average. Mean of square of velocities we have taken. So C square is equal to C1 square plus C2 square plus C3 square plus C4 square plus so on Cn square divided by n. And if you take C now here, C is equal to, we take under root. So C equals to under root means square root of mean. Mean means average. So square root of mean of square of velocities. So what is RMS full form here? Root mean square. Root mean square. That means what now here? Root of mean of square of velocity. Root of mean of square of velocity. Okay, so C is equal to what? Under root C1 square plus C2 square plus C3 square plus so on Cn square divided by n. So this is what now here? RMS velocity. So RMS velocity. Thus, RMS speed. RMS speed is defined as the square root of the mean of the squares of the speeds of all the molecules present in the given sample of gas. The given sample of gas, the square root of mean of squares of speeds we have taken. So the value C is defined as determined by formula what now here? C is equal to, C means for RMS only here, remember. So we can write C, otherwise URMS. In some books they take VRMS, V otherwise U. So URMS otherwise C simply. So here RMS velocity is equal to under root 3 PV by M formula, 3 PV by M. That is equal to, here PV is equal to R for 1 mole. For 1 mole, PV is equal to RT. In place of PV, what we can write? RT we can write for 1 mole. So 1 mole means the small n is equal to 1. So for 1 mole of the gas, PV is equal to RT. In place of PV, what we can write now? RT we can write. So 3 PV by M we can take. Otherwise, under root 3 RT by M. Otherwise, now here see one more thing. Now here, P by D, why we have taken generally density is equal to what? Mass by volume. Mass by volume. And what is here 1 by D? 1 by D is equal to 1 by V by volume. V by mass. Now if you take V constant here, now how D and M related here? Directly related. So that's why what we can write now here 3 RT by M. Now in this case you see V by M. V by M is here. So M by V is D, but V by M is 1 by D. Okay. V by M is what now here? V by M is 1 by D. So in place of what now here V by M, in place of V by M, what we can write now? 1 by D. So 1 by D we have taken. So 3P into 1 by D. In place of V by M, what we can write? 1 by D. That's why 3P by D. 3P by D. So the formula of the different formula of RMS velocity what here? RMS velocity is equal to under root 3 PV by M or 3 RT by M, under root 3 RT by M or under root 3P by D. Any formula we can use here. So it is about what now here? Formula of RMS velocity. In SI units, MKS system. Okay, the values of R means the universal gas constant, pressure of gas, volume of gas, molecular mass of gas, density of gas are used like this. R value what now in SI system? Joules. In joules we have taken 8.314 joules, Kelvin inverse, mole inverse. In joules we have taken MKS system. Okay. Otherwise we can take R value 8.314 into kilopascal into decimeter cube. Kilopascal into decimeter cube. Decimeter cube means liter only. 1 decimeter cube means 1 liter here. Okay, so kilopascal, decimeter cube, Kelvin inverse, mole inverse. So in this units also the same value 8.314. And V is what now here? Velocity, volume of the gas. Volume of the gas is always in liters. Volume of gas should be taken in liters. And P is what now here? Pressure. Pressure of the gas in kilopascal. Kilopascal. And here 1 atm generally equal to how many kilopascal? 100 kilopascal you take round off. 101.3 means here you take 100 round off. 100 kilopascal. 1 atm is equal to how many kilopascal? 100 kilopascal. So the pressure you take in this formula as kilopascal. In kilopascal we have taken. 1 atm is equal to 100 kilopascal you take. Okay. 3 atm is equal to 3 into 100. 300 kilopascal. Like that you convert atm into pascals. Okay. So it is P, pressure. And also M is what now? Molecular mass in kilogram we have to remember. We should not take in grams. Suppose you take O2 gas. For O2 gas, gram molecular mass is how much? 32 grams now. 32 grams per mole, right? But here grams we should not take. We should convert into kilograms. We have to take 32 into, in place of gram, what we have to take? 10 power minus 3 kilogram. 1 gram equals to how many kilograms? 10 power minus 3 kilograms. So like this, 32 into 10 power minus 3 kilograms per mole. So this value we have to take. 10 power minus 3 we have to take. 32 into 10 power minus 3 kg we have to take in place of M for oxygen. So we should not take directly in grams, remember this point. And D is density. Density in kilogram per meter cube. Now density should not be taken in gram per cc. Remember. Now suppose density is in centimeter, gram per cc suppose. Gram per centimeter cube. How to convert this one into kilogram per meter cube? 1 gram is equal to what? 10 power minus 3 kilograms. In place of gram, what we have write? 10 power minus 3 kilograms. In place of centimeter cube, how many meter cube? So 10 power minus 2, 10 power minus 6 meter cube. Okay, 1 centimeter is equal to what now? 1 centimeter is equal to 10 power minus 2 meter. Na? So centimeter into centimeter to centimeter. Okay, 10 power minus 2 into 10 power minus 2 into 10 power minus 2. 10 power minus 6 meter cube. 10 power minus 6 meter cube like this. Suppose the same thing out right now. 10 power minus 3 kilograms by, in place of centimeter cube, what we write? 10 power minus 6 meter cube. So this conversion we have to take here. The gram per centimeter cube we have to convert into kilogram per meter cube. Is that clear, ma? So these units are very important in this formula. Okay. Next, another one is what now? Average speed. First one is RMS velocity, RMS speed. The second one is average speed. So it is arithmetic mean of various speeds of the molecules. Means what now? Arithmetic mean means average. Average of different gas velocities. Now, average speed. So average speed is given by the formula what? Velocity of first molecule plus velocity of second molecule plus velocity of third molecule plus so on, velocity of nth molecule. Suppose n number of gas molecules in the gas divided by n, total number of gas molecules. So this is what average velocity or average speed, and it is equal to what? Under root 8 RT by pi m. So average velocity, U average is equal to what, man? Under root 8 RT by pi m. U RMS, what we have written? U RMS is equal to what? Under root 3 RT by m. That point keep in mind. So U average how much now? Under root 8 RT by pi m. Okay, man? So generally R value how much here? R value 8.314 joules we take now. So this value generally we can take easy to calculate. 25 by 3 you take here. 25 by 3 how much now? Nearly 8.314. So instead of writing 8.314, 25 by 3 if you substitute here in place of R, it will be easy for calculations, remember. Okay, ma'am. So now here U RMS is equal to under root 3 RT by m, whereas U average is equal to what? Under root 8 RT upon pi m. Under root 8 RT upon pi m. Pi is what? 3.14. Okay, 22/7. So like this, we take now here what now here the different types of velocities. Now it is related to RMS velocity, the average velocity. It means what here U average. So U average is related to RMS velocity by the following relationship. So average velocity is equal to 0.9. You remember 0.9213. You can't remember 0.9. You take 0.9 into RMS velocity. Okay, so URMS. So U average is equal to what, ma'am? U average is equal to 0.9 into RMS velocity. So this only remember. If you remember this one, automatically you can take this one, no problem. So if you take what RMS velocity is equal to what? This average velocity by 0.9213. Then you will get this one. Both you need to remember. This one remember mainly. Okay. Now here, this formula is important, and I told you three types of velocities. Now, what are the three types of velocities? This average velocity, RMS velocity, and also what we have, most probable velocity we have. Most probable velocity also we have. So now only remember here it is what relation between average velocity and RMS velocity. What I told you, average velocity is equal to 0.9 into RMS velocity. Na? The same way, if you take most probable velocity, so U most probable means most probable velocity is equal to 0.8 only take 0.8 into URMS. So this also remember now only. We are going to study this one, but remember. So U most probable means most probable velocity and RMS velocity, how they are related. UMP is equal to 0.8 only, 0.8 into URMS. Here 0.9 into URMS. That point keep in mind. So if you take average velocity and most probable, which one generally has more magnitude? Average velocity has slightly more magnitude than what? Most probable. RMS velocity, average velocity speed is greater than what? Most probable, slightly. That is why here most probable we got 0.8 here, less value, and average velocity we got 0.9 here. 0.9 slightly more than 0.8 na. That way we remember here. So in general, whenever you recall this formula, you confuse 0.8 and 0.9. 0.9 is for which type of relation? 0.8 is for which type of relation? You may confuse sometimes. So that's why I'm telling you that 0.8, 0.9, which is greater value? 0.9. Most probable velocity and average velocity, which is greater magnitude in magnitude? Average speed only slightly having what greater magnitude. That's why average velocity is equals to 0.9 into RMS velocity. Most probable velocity is equal to 0.8 into RMS velocity. Okay, so this relation remember now only. And this one need not remember again. Don't remember this one again. You will confuse. From this one you will get average speed equals to 0.9 into RMS speed. Then RMS speed is equal to average speed by 0.9. That's what we got here. Okay. So it's about what now here? The important areas of what now? Two types of velocities we studied so far. And average speed, one more point, take it here. Average speed is equal to 0.9, they give C directly. 0.9 into RMS speed. And RMS speed is equal to this one. Anyhow, this step. So most probable speed is what now we are going to discuss tomorrow, this one. So most probable speed is nothing but this is defined as the speed possessed by maximum number of molecules of a gas at a given temperature. At a given temperature, okay, the velocity which is possessed by very large number of gas molecules is called what? Most probable velocity. Most probable velocity. Otherwise, let us go with this one. Now, most probable velocity is equal to what now here? Under root 2RT by m. Most probable velocity formula what? Under root 2RT by m. Okay, ma'am. So next, this is related to RMS speed by the following relationship. Most probable speed is equal to, okay, so under root 2 by 3 RMS. Under root 2 by 3 RMS means what now? What I told you? 0.8 into RMS I told now. RMS velocity into 0.8 is equal to most probable speed. From this one, we get RMS speed is equal to what now? Most probable by 0.816. We'll get this one. So remember this also. Already I told you this one. So this is about what now here? Most probable velocity. Okay. The three kinds of molecular speeds are related to each other as follows here. So most probable is one, most probable, and it is average, and it is RMS. A formula we know, under root 2RT by M east, under root 8RT by pi M east, under root 3RT by M. So from this common is what now? Square root 2 here, square root of 8 by pi, square root of 3. So square root of 8 by 3 means what here? Square root of 2.5 approximately. Square root of 2.5. It is square root of 2. It is square root of 3. Which one has more magnitude now? Square root of 3 will be having more magnitude, right? So now here, if you take the ratio of these three velocities here, 1 is to 1.128 is to 1.224. So what is the relation here? U MP, the ratio of UMP, U average, and U RMS. So this ratio you take as what now here? 1 is to 1.1 is to 1.2, enough. 1 is 1.1 is to 1.2. Is that clear, ma'am? Which one has more magnitude here? RMS velocity has more magnitude. Least magnitude, most probable velocity. So this way we have to understand concept. Okay, ma'am. So this is about different types of molecular speeds. And it is important bit here. The ratio of what? Different types of molecular speeds. Okay, ma'am? Bye. Good day. Take care.